Happy Virtual Day. We will be doing lesson 4.5 and kind of a nice, easy lesson. It's more of a formula, so once you understand how to use the formula, this one isn't too bad here. Alright, so our two topics today are going to be linearization and differentials. They actually work hand in hand. It's solving the same problem just in two separate ways. So when we think of calculators can do a lot of things, but we don't quite understand everything that's programmed in them. So for example, if we had the function the square root of x, we obviously know that if we plug in 4, our output would be 2. But without a calculator, how would we find what 4.1 is? Or I guess even with a calculator, because we're going to use our calculator this whole section. Even with a calculator, how does a calculator do problems that are not exact? So let's think of this as a picture really quick. So the square root of x would look like this. Right, just some curve like that. So what we want to do is we're going to call this our center. Whenever we approximate, we use our center point. So that's a known point, but we want to know what's happening at, this is 4, like right next to it at 4.1. If we want to use our known point to estimate our unknown point, but it's really close to it, we could use our tangent line. So we would say we have our point, we need a slope, so when we plug in y minus 2, we'll leave the m spot open now, and we'll solve that with our derivative. So we'll do f prime of x, change this to a 1/2, x to the 1/2 power. So we'll drop that 1/2, subtract 1, and then this would be a time I think it would be helpful to simplify, because now when we plug in a number, we plug in our 4 here to find our slope at 4. So when we plug in 4 for x, we get 1 over 2 square root 4, which is just 1/4. Now normally we leave our tangent line here, but again, this would be a time where we maybe want to simplify this. We distribute that 1/4. If we distribute the 1/4 there, that's -1, and then add the 2 over. That is our tangent line, just in slope-intercept form. So we have y-intercept of 1, rise of 1, run of 4, and so forth. We want it to go through the point. That's what tangent lines do. They go through the point on the graph at one point. Now this tangent line isn't actually touching f of 4.1, but we can see that it is so close on our tangent line. It is almost, that yellow dot was really tiny. We can see that on the tangent line it is almost exactly at 4.1. And so that's where we can use our tangent line to estimate values on an actual function, knowing that it is an approximation, it's not exact. So if we want to know what 4.1 is, we could test this out and put 4.1 in here and then bring over that plus 2. This is where it's funny because I'm going to let you use your calculator. Like you could have just put square root of 4.1 in there, but this is actually the math your calculator is doing to get the answer. So when you throw this in your calculator, you get 2.025. But again, that is an approximation. So f of 4.1 approximately equals 2.025. So, oh actually that was all in this section. No wonder why there was not a lot of room. Let's actually find in part C the actual value of 4.1. If you actually square root 4.1, and we'll round it, it's 2.02484. our approximation was pretty close. So this is the actual, this is the approximation. So our calculator will do this with little to no error. Sorry, I did not realize my screen cut off. There we go. Your calculator will do this with little to no error. 0.1, going from 4 to 4.1, that was actually a big jump, even though 0.1 is not that much. Your calculator would do this as the limit as the change goes to 0, and then that's actually how it gets this actual amount. But this approximation was pretty spot on. Alright, as for this bottom section, we are going to skip most of it. I just want you to know one part of this, and it's already cut off the one part I want you to know. Alright, here we go. We're going to skip all of this just to save time on the video. I think you don't need that to understand today's lesson. But this word differentials. We've said something is differentiable if you can take the derivative. So anytime you see some form of that, you're thinking dy dx. But today we are going to look at these as separate things. We've always looked at it as dy dx, but we are going to look at what is the dy talking about and what is the dx talking about. So think of them as separate terms. Go ahead and flip your page to the back side. Okay, so we are switching to the idea of, or we just did linearization. Now we are doing something called differentials. So differentials allow us to treat dy and dx as separate terms. So all we have to remember is that dy dx is a small change in the y. I'm sorry, just dy is a small change in the y, and dx is a small change in the x. We are talking about two variables, the change in both variables. So if we wanted to derive example 3 how we always have, we can say dy dx equals 15x squared minus 6x. No different than what we have. But another way we could write this is to multiply both sides by dx, and notice I'm putting this side in parentheses. If I don't, it looks like we're just multiplying the 6x by dx. So we could actually rewrite this as the change, the specific change in y is the derivative times the specific change in x. And we can look at them as separate variables. Why might we want to do that? Well, when we take a look at an example like number 4, again, this is all about approximation. Yes, we could use our calculator on all of this, but this is the math the calculator is doing to get a value. So we are given, we want to find the differential. We want to find what dy is when the change in x is this, x is 2, and this is our function. So let's first just derive our function. And then we saw in the previous example, we can actually multiply the side by dx. And so this is the information we're given. So from here, let's just plug in what we know. We don't know dy. We want it at x of 2. And our change in x is 0.01. Again, this is funny. Throw it in your calculator. We could just use our calculator in the first place, but this is, again, the math that's going on in your calculator. So throw that in and see what value you get for dy. Alright, you should get the change in y to be 0.32. What did we actually just do, though? Well, here's actually what happened. It's very similar to the front. This is all about approximating things. We found when x was 2, if you plug x into our original function, you actually get the 0.20. What we did was we found a small change in the x and a small change in the y. So our small change in x was 0.01. So what we are doing, we are approximating the value at 2.01 in this function. So by changing the x, we calculated what the change in y would be, which we just calculated to be 0.32. So we are approximating that 2.01 has an output of 0.32. Again, it's not exact, but this was a pretty good approximation, because now let's actually find the actual value. The actual value, the function at 2.01, let's use our function and plug that in and see what you get. Okay, so when you find the actual value at 2.01, it is super close. We estimated that it was just 0.32, but I cut off my decimals. 0.3256 was the actual amount. So then we could do what the error was, and the error of something is the actual minus the predicted. So if we wanted to find our error, our actual is 0.3256, we could subtract our predicted y value of 0.32, and then we would calculate the error that way. So again, all about approximating things today. Okay, taking a look at example 5, we want to use differentials to estimate the cube root of 29. Find the error in your approximation. So again, we could just throw this in our calculator, and we'll do that later. But if we didn't have our calculator, we would want to use some sort of cube root that we know. And you may not know your cube roots well, but maybe you could figure out that we could figure out something super close to 29 that we know the cube root of, and that is 27. So the cube root of 27 is 3. So we are going to use the fact that the input of 27 got us the output of 3, because that's at least really close to 29. Once we know a point, we're going to use the known value to predict to approximate the unknown value. So this function, we've always been given a function in every example so far. Sometimes if you're not given a function, you just have to know that the function came from this. 29 was just an input, but this is really the cube root of x. So this whole time we've been saying, let's find the change in y, let's find the change in x, and we'll change this to x to the 1/3 power. So we'll drop that power, and then when we subtract 1, we're subtracting 3/3, which gets us to be -2/3. So now when we simplify this, we have the cube root of x squared. And then remember, we can bring that dx over. Oh, I'm sorry, this side should be dy. So the change in y is this. You always use your known numbers for the prediction. So this x, we are going to use 27. It will approximate 29. We'll see why in a moment. So when we plug in our 27 there, we have to figure out what is our dx. And that's where now we look at this 29 and we say, oh, our change in x was by 2. Because from 27 to 29, that is 2. So the known to the predicted is that change in x. And so we'll throw this in our calculator, and we will get that dy is equal to 0.074. So now, I always like to do the ordered pair. Our known value is 27.3. We want to add on our dx value. We want to add on our dy value. We said our dx value was 2 to get to 29. And then we just calculated that the dy value is this.